Cool.
Okay. Okay, let me click on OK up here. All right. So one of the students' questions was, as a matter of fact, about this was how did the sun actually work, and why does it get hotter with time? And I think I addressed that in the first talk. So that'll be very easy. I don't know if you two are interested in that, but the sun is a mess of hydrogen, helium, and so it obviously has gravitational energy compressing it, and it's the same thing's happening on Earth. That's why the core of the Earth is about 5,000 degrees because of the pressure of gravity compressing the center. And in the sun's case, since it's much bigger, the plasma core temperature is almost 16 million degrees, which is not quite enough to ignite fusion, but not every um, hydrogen ion in the sun is exactly 16 or 15.7 million degrees. And so there's a tail distribution. So some of them get to be 100 million degrees is what you need for fusion. Fortunately, not too many because then the sun doesn't go supernova really fast and it doesn't just blow up. So in fact, the release rate per cubic centimeter is quite a small amount of energy. Of course, the sun is very large, so it turns out to be a lot of energy in total, and it will last a long time because but it does gradually get warmer because when four hydrogen ions fuse to become helium, that means four individual, if you think of it as a gas, gases particles. There's, the pressure is proportional to the number of particles. So the outward pressure gets reduced because now you only have one particle instead of four every time there's one of these fusion reactions. So the gravity can compress it even further, and that heats it up, and that that extra heat means that the sun creates more energy, so it gets hotter with age. They asked the question, so I thought maybe you folks wanted to hear that too. At any rate, the surface of the sun is 6,000 degrees, so it's um, a hot reservoir, and the empty space is only 2.73 degrees, so it's a cold reservoir. And so we have an intermediate temperature and we can dump heat. And so this is exactly the way a steam engine works, or a nuclear power plant, or anything. Everything on the surface of the Earth, all the processes, the wind blowing, evaporating water, and so forth, everything here runs on solar energy. So that means the Earth is a dissipative heat engine. It's a heat engine, obviously, but it's dissipative because it's dissipating this energy. You can't reverse this process. And the human economy, which is entirely embedded within the Earth system, is also a dissipative heat engine. Okay, so we're here, possible futures, energy, and the environment. So we went through all this stuff, and so we know we're in a great deal of trouble, and we know we don't have a good economic system. And then just confirmation that thermodynamics is important. A quote from Albert Einstein, a quote from Arthur Eddington, and energy conversion, entropy production do determine the growth of wealth. That's Rainer Kummel's second law. He's a physicist, but he wrote an economic textbook. So we have six big problems: ecological collapse, and we saw that, and climate change. And we have an enormous amount of weapons of mass destruction. And neoclassical economists have the wrong model of the economy, which is physically impossible, and they are deciding policy. Capitalism encourages dishonesty, rewards greed, promotes psychopaths, and requires exponential growth to function, which is impossible. And so, but what is the alternative to capitalism? And everybody thinks, well, if you say anything bad about capitalism, you're obviously a communist. It's like there's a whole spectrum of possibilities. And I think humans are suffering mass psychosis because they're just unaware of all these pressures. So this paper was written in January 2024, so just about a month ago or so. What the authors speculate is we're on path B and we're heading for biosphere collapse. That's obviously true. And there's two possibilities from there. The biosphere could collapse and we can have dieback and then just keep going, or we can the stress, because agriculture will disappear. We can then just extinct ourselves because we have weapons of mass destruction. There is a path A though. Otherwise, why would I even bother to have conversations like this? And so we need to get off of the path we're on and get onto a path A, which leads to a global sustainability. But part of that is recognizing that we waste an awful lot of energy. So let's see, let me move this around. Yeah. So this is the energy needed for 8 billion people to have a decent life. And here's how much energy we're burning every year. And yet, despite the fact that we're burning 4.5 times more energy than we might actually need, we're not giving everybody a decent life. And when we talk about how difficult it will be to replace all this energy, I'm talking about up here. But you can imagine if we reduced our energy, even kept it double what we need for everybody to have a decent life, there's no reason why we couldn't, by having a different system and reapplying that energy and having different priorities, afford everybody a decent life, even with still some waste. And this would be a much easier target for us to reach. Instead of building out these tiny little bits of solar, wind, and hydro and everything to replace all of this, we could make it a more achievable goal. And by the way, coal is grew by a factor of 10 over anything else since 2000. Oil was the fastest growing energy source in 20. I thought I changed this in 2022, which is the latest data that's accurate. So 2023 data is not completely printed yet. So oil was in the last year we had was the fastest growing energy source. Okay, in absolute terms. And there's projected growth. I mean, EIA projects 50% growth in total primary energy by 2050. And that would be about this much if that happened, and that's what we would have to do. We would have to replace all of that. And even if we cut 5% per year from our emissions by 2050, we would still be putting 7 gigatons of carbon dioxide in the atmosphere just due to our energy, not including land use changes. And that doesn't include a lot of methane, and it does include a lot of nitrous oxide. This is an interesting statistic, and this is how efficient the economy has become. This is from the IEA, and I had data from about 1970 to about 2017. So I plotted it here. But all during the time we were making the economy more efficient, we were burning more energy. Underscores the fact that efficiency gains do not reduce energy consumption. The growth in nuclear power, in 1970 to 1980, it grew by about 30% per year for a while, for a decade, and then it fell off. And now it's only 2% of global energy consumption. And yet here coal is, our largest energy source. Why? Okay, well, the cost. And so when we talk about solar and wind, it's going to require batteries. The best batteries technology available today is lithium. This is the average price of lithium in 2010 to 2022, 2023, and it grew by a factor of 10, and it just went skyrocketed. So when we say, okay, we have this exponential growth of nuclear, yet it stopped growing after that, probably because of the cost. And and uh, and and the transition to solar and wind may face exactly the same. We may see this play out. Maybe not. Maybe there'll be a miracle. But the point is, you can't just assume because solar and wind are growing at high percentages that they'll continue to do that. Um, Renewables are not even the cheapest form of power. This is Art Berman. So wind with backup, and that's the critical thing. If you right now, when everybody says solar and wind are cheap, they're not accounting for the fact that they're intermittent and you need batteries to back them up. Well, we don't have those batteries, so mostly we're using natural gas, what's called natural gas peaker plants. So if you just ran natural gas by itself, it would be one of the cheapest sources of energy. But because natural gas is such a good source of energy from the point of view of matching demand, it's used as peaker plants to so when these guys go out, you have gas. And these guys can be as intermittent as you want, but as long as you have natural gas backing them up, you're fine, and you can maintain the load in the on the grid. And you could see that yeah, nuclear is not, for some reason, not that expensive, at least according to this study. And so there's three lessons from our experience. These are things we've experienced, right? We've never replaced an older energy source with a new one except for slavery and whaling. And we achieve both of those by standards, regulations, and moratorium and force. So the idea that just building out solar and wind and that's magically going to replace anything else is not really, it's not backed up by any kind of experience that humans have had. Efficiency has never reduced energy consumption. We saw that. And there's a proposed fourth law of thermodynamics by ecologists called the maximum power principle. And so what an organism, like a superorganism like humanity, does is it will maximize its power throughput. So just because you add another source of energy doesn't, it's still going to maximize the amount of power it can flow through the system. And as William Stanley Jevons wrote, it's a holy confusion of ideas to suppose that economical use of a fuel is equivalent to a diminished consumption. He wrote the very contrary is true. And also, finally, an initial pulse of exponential growth may not be sustainable as demonstrated by nuclear. Now, here's just to give you a feel for why should Jevons paradox be true. When the steam engine, the first steam engine was Newcomen's atmospheric engine, and you can see it was like a building. It was a big thing, and it was only, you built it at a site of a coal mine, and it was used to pump out water, so the coal miners could continue to operate. It's very impractical. It was very inefficient, and there was no other use for it. But then all of a sudden, you make it more efficient, you streamline it, make it more practical. You can put it on wheels. So the more efficient we made steam engines, the more uses we found for them. And so we used much more coal until today. Turbine generators are pretty efficient. Talk about nuclear. So nuclear comes in two flavors. What we actually, here's my face. What we actually do now is called fission, and we fizz uranium or there's one thorium reactor presumably in China, but other than that, I don't know of any. But we do have about 450 uranium reactors, and that takes advantage of the fact that if you go up to this plateau here with iron, copper, cobalt, nickel, and so forth, you can gain energy because these are the most stable nuclei. They take the least binding energy. So these take the more binding energy. So if you go back in this direction, you release that binding energy and it becomes available for to do work. The same thing is true here. So you go from hydrogen and helium up to iron, you release energy, and that's how stars work. And of course it works, even though we're talking about little tiny bits of energy, E equals mc squared. So you're multiplying that small amount of mass that you're actually losing, and converting it to energy, you're multiplying it by the speed of light squared. So the atomic mass of iron is 55.8, yet iron's atomic numbers are 56, 57, and 58. There are 3 stable iron isotopes, all larger than 55. Hydrogen has a atomic mass of just slightly more than 1. So you you take 56 of these, you get a lot less mass. Fission is a spontaneous at all temperatures. And so in the first lecture, we learned that it had a half-life. U-238 has a half-life of 4.5 billion years. U-235 has a half-life of about 700 million years. So they'll decay on their own. If you have a clump on your desk, it will eventually become thorium and eventually go into lead. You will die before you will notice that, but still, it's a spot. All you're trying to do is take a reaction that will happen anyway and speed it up. And the trick is, and maybe why they're so expensive, you're trying to control that, speed it up enough to boil water, but not so much that you blow yourself to pieces. And so it's a control theory problem, to try to control that reaction such that you're in that sweet spot, but you don't go too fast, and if you go too slow, of course, you don't generate any energy. Fusion is not spontaneous at room temperature because the activation energy required to overcome. See, deuterium has a positive charge and tritium has a positive charge. So you're trying to push 2 positive charges together. It's trying to push 2 north poles, 2 magnets, the north poles together, right? You just can't do it. So you're trying to, that's called the Coulomb force, and you're trying to overcome that. And that's why you need to heat these guys up to 100 million degrees under pressure. When you do, you generate helium, you generate energy, and you release a neutron. This neutron hits the reactor vessel, and so when you and causes radiation, it causes to become radioactive. So it's not true that nuclear fusion has no waste. Okay, it does. It has considerable waste. It's just that it doesn't have the really seriously bad waste that fission has. So this produces things like plutonium, which has a very long lifespan. So you're talking about 10,000 years you have to bury that stuff. But this waste you only have to bury for 100 years. So it's not as bad. But still 100 years is not good either. Now, the problem is we need to combine deuterium and tritium. So that's the fuel. So because this is the reaction rate, and deuterium and tritium have a reaction rate that's 2 or 3 orders of magnitude more than 2 other possibilities, deuterium, or deuterium, helium-3. And in order to get the same kind of reaction rate, this is temperature. So you get this at 100 million degrees. For these guys, you got to get into billions of degrees. And obviously, that's difficult to do. Now, deuterium is plentiful. 0.02% of all hydrogen on Earth is deuterium. But tritium it doesn't exist on Earth naturally. And in fact, we have a total amount of tritium reserve of 20 kilograms, which is, but ITAR, when that's the big fusion reactor they're building in France, that'll use 300 grams every day. So that's about 2 months worth. They'll burn through the total store of tritium in 2 months. Also, tritium has a half-life of 12 years, and so again, like I said, it doesn't occur naturally on Earth. So, uh, fusion is not necessarily I mean, just because they get this reaction in here and there, and they have some successes, they nobody knows how to do this or where they're going to get this tritium from. This tritium is manufactured in fission reactors, so it's a byproduct or a waste product of fission is tritium. um okay, so let's flip and now talk about this is Electric Power Portfolio in Ottawa, Canada, and it's over 5 days, and they get most of their energy from nuclear. The next biggest is hydro, and hydro goes well. Hydro you can meet the demand. So this thing is demand is daily, right? During the day, uh, and then during the night it falls, and then during the next day it rises and it falls, and you can balance some of that by controlling the water flow in your hydroelectric thing. But the big control is coming from gas, right? The gas can match it perfectly, and in this 5 day period there was very little wind. And then at the last day there was a lot considerable wind. So you can see that gives you an idea of if you were running just on wind, the intermittency. I mean, most of the time it isn't very windy at all. This little tiny blip is solar. And of course, this is February, so you wouldn't expect much solar, but that highlights the fact that in the summer, you probably get a lot. And so you get the seasonal thing. And so you need quite a bit of storage to make up for the fact that solar is only going to happen in your spring, fall, and summer, and the wind is intermittent. A lot is said, like in Europe, they'll argue that, well, okay, when the wind isn't blowing in Spain, it's blowing in Germany or something. But that's not really true. So under this example, in October 2015, this is it turns out these are different countries, and the wind was blowing pretty much everywhere at the same time, and you were having these gaps where no wind was blowing anywhere. So it can't even back up itself spatially. Michaud, Simon Michaud, he estimates that you need battery storage. You need about 4 weeks, but he doesn't think this is enough. Okay. And I agree with him. Princeton University came up and said you only need 6 hours. Well, 6 hours is a joke. You need more than 6 hours. Okay, let's switch gear a little bit. This is extra power capacity. You need to phase out fossil fuels, so you need to ramp things up quite a bit. And this is from Simon Michaud, but he even admits he's not desalinating any water. And by 2030, we estimate we're going to have a water shortfall, which if you got it from desalination, you would need 6,000 terawatt hours. Energy required for DACs would be something on the order of 24,000 terawatt hours if you were still burning the amount of coal and you tried to get to net zero, you'd have to be wasting considerable amount of energy. Emissions-free cement requires additional energy. That's not included here. You could do it, but you require more energy to do it. Nothing comes for free. And this does not include energy used by industry in the form of heat from natural gas and coal. Okay. So transport electric cars use more minerals than a conventional car by like a factor of 6. Copper and lithium, nickel. Nickel's a big component of this. Manganese and so forth. This is graphite, I think. So when you go from a conventional car that doesn't need a whole lot, well, minerals, and you're going to an electric car, you're really ramping up the amount of minerals you need. The same is true for power generation. Offshore wind and solar need more minerals than natural gas. So copper, if we try to, okay, this is battery metals needed to phase out fossil fuels. This is just one of Michaud's scenarios, and this is for both vehicles and power storage stations. This is the global reserves. This is the amount that you will need, and you can see, okay, copper, you're going to use quite a bit of the copper, but nickel and cobalt and lithium and graphite, you're exceeding your reserves. This is another view of the same thing. Quantity of metals needed to manufacture one generation of renewable technology units to completely phase out fossil fuels. And even copper see, this is scenario F, and I don't know what scenario F is. You'd have to read his book. Oh, he's increasing hydropower by a factor of 4, and that's not going to happen because all the dammable rivers have been dammed, and so now you get rid of that, and this goes up. But anyway, this is the total metals you need, and then this is the reported reserves, and this is the metals production, total metals production in 2019, and this is orders of magnitude, right? 100,000, 10,000. So there's an order of magnitude gap or 2 orders of magnitude gap in lithium in what you need compared to what we have. Now, I think this is amusing. I found this on the internet, and obviously it was put together by somebody, I'm in the automotive industry or the gas or oil industry. But anyway, so this is a lithium mine, and because nothing says I care for the planet like a battery powered car, right? Except I recognize this, and anybody who spends even a little bit of time like me being concerned about these things know that that's not a lithium mine. That's actually a copper mine, and it's the Escondida copper mine in Chile. It's a very well-known copper mine, and it's pretty straightforward. So there's so much misinformation. So people are showing that, blathering that all over the place, and believing it. Not that's copper mine is any better. It's still pretty unsightly mess, and this is huge. Mark Mills, according to Mark Mills, the IEA says we need hundreds of new mines like this, and if that's true, I don't know that that's true. But the report, the IEA report, is behind a paywall. You have to buy it, and Mark Mills bought it, so his word, I guess I have to take it. This is a lithium mine, and this is in so lithium doesn't look very pleasant, as a thing to mine. The historical projections for copper mines, that we're going to run out. We're going to peak in about 2035. Well, here's where we are now. This was the projection, so we're not quite using as much copper as what was forecast from this thing. So I don't know what to do with that. Um, then Simon Michaud shows the periodic table of elements and says, look, there's 92 elements. You can't replace all of them with other things. And so this idea of infinite substitution is which actually some economists believe is just not true. I mean, we're already using the best materials for the best, copper. We're using that for all our because it's the best. And what do you replace it with? Gold, silver, or platinum? Platinum should be on this line somewhere. Okay, so again, we have a minerals shortfall. This is again another paper from Art Berman. He believes that in November 2018 we peaked, and we've actually since August 2022 we've come back up in total, so we've actually above this. But where we made up for that is in natural gas. The peak for 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 um, for crude and condensate is still the peak. So we haven't gotten that high yet. Again, and this is biofuels, and this is natural gas liquids. And biofuels is a disaster in its own because you're taking lands. This is corn ethanol or soybeans or palm oil. And so that land could have been growing food, or it could have been reserved for wildlife, so we wouldn't be running out of be killing so much wildlife. Okay, everybody wants to be Norwegian. um it's kind of funny. 80% of new cars in Norway are EVs now, and that's because they have a government subsidy. Each EV imports 134 gigajoules of fossil fuel energy, and it's manufactured. They don't actually manufacture them there. 100% of electricity in Norway happens to be renewable. In fact, it's all hydro. All of their electricity is hydroelectric. Norway and Costa Rica have the unique advantage of being relatively small countries, low population, having lots of mountains and lots of rainfall. And so they both generate all their electricity by hydroelectric. And that's 72% of all their primary energy is hydro. Okay, it's not solar and wind. Because they have $25,000 per year per capita revenue from their oil and gas, they're a very rich country. Not many countries are as rich as Norway, and it's got 3.7 times the world average GDP per capita. And I think it's more than the United States. Okay, so you can't just point to Norway or even Costa Rica as an example. Oh, see, they do it. Not everybody has those circumstances, those fortunate circumstances. Okay, hydrogen. There's a lot of talk about hydrogen being a fuel. It has several problems. It's the molecular hydrogen is rare on Earth, so hydrogen must be manufactured. It is not an energy source, but a storage medium. Okay. So basically 95% of hydrogen now is black. That means it comes from fossil fuels and emits greenhouse gases. And hydrogen is very important in the chemical industry because it's used for a lot of chemical processing. And it's virtually all, and that's why they do it at all, because if you're using it for energy, you wouldn't, obviously you would just burn the fossil fuels because it's so inefficient, right? To burn the fossil fuels to generate hydrogen. And basically hydrogen is from natural gas with carbon capture and storage. This is what they propose to do. And in the end, the claim is that produces as much greenhouse gases because the carbon capture and storage requires energy. And anyway, there's leaking hydrogen. Hydrogen, as it turns out, a greenhouse gas. So producing hydrogen from solar and wind is more expensive and more inefficient. Nobody does it. Okay, cold start problem. Because the fuel cells produce water and water freezes below 0 degrees C. In the winter, you have a problem. They don't know how to solve this. Okay, you can do it in a warm climate, but in a colder climate, this is problematic. Proton membranes are made from platinum and iridium, and these elements are rare and expensive. Hydrogen is a small molecule, and it creeps into tank walls. and it comprises their chemical structure and makes them brittle. This is called hydrogen embrittlement. Okay, so the tank walls for hydrogen don't last that long, so you're constantly having to replace them. Okay, these are the sources where I learned all this stuff. Okay, the way energy is handled, there's primary energy, and then through the conversion processes, you have losses and secondary energy, electricity here, and then you distribute it. You get losses over power lines, and then the end uses. This is final is what's distributed to your house, and useful energy is what you actually use. Your end product, and if you think in terms of light, you start with coal in a power plant, you generate electricity, then you put it on a grid, you lose some, and then the radiant, most of the light bulb energy, much of it is heat. I mean, LEDs are pretty efficient, but the energy that you use is actually just the radiant energy, the light. And here's an example for gasoline in a passenger vehicle. So that's just the, but I think, so when we talk about, a lot of talk is about, well, okay, you're starting with heat energy, and we're going to replace that heat energy directly with electricity. And therefore, we're going to save this much energy. We don't actually have to build out build this out with solar and wind. Well, except you have to build out at least that much, if not more, to capacity to make up for the summer winter problem and so forth. But this is a really good idea, and I think it's a good idea because we have all these coal-fired power plants, and most of them are less than 20 years old, because the older ones have been replaced or phased out, and so this infrastructure exists, including the power lines and stuff, but they're running on a boiler. And what you can do is replace it with one of these devices, and so you have solar and here, and you generate electricity. You put it right on a grid, but also take it and convert it to thermal energy. And then of course, when this, at night, have all this thermal energy, and then you just reuse the power plant all over again. So the point is you're not really eliminating those inefficiencies of going from electricity to thermal back to electricity. And this is a desirable thing to do because this infrastructure already exists. And apparently this is a product you can buy. Okay, energy demand to pull carbon dioxide out of the atmosphere. I have better numbers for this, but the main thing is 24,000 terawatt hours in my simple example. And I got this information from Jennifer Wilcox. She's actually one of the advisors to Biden but when I talked to her, she wasn't in his energy plan, and she, that's where I got this number to pull out 1 million tons of carbon dioxide per year requires the entire output of a 300 to 500 megawatt power plant for running the whole year, just to get 1 million tons. And so I sent her these calculations I did, and I asked her, am I making a mistake? And she says, no, I don't think you miscalculated. It's just that what's required is quite significant. Direct air carbon capture and storage is one component and not a silver bullet. And the problem is there is no silver bullets. Then she says it could be done with natural gas, and we can capture the CO2 from the natural gas, but you take so much energy, you're better off just burning the natural gas for energy and forgetting about that, pulling the carbon dioxide out of the atmosphere. We don't know what to do with it. She sent me a whole bunch of papers to read. We do not actually have a scalable plan to store it. And then if we wanted to replace all that energy with nuclear, we'd have to build two every day, and we're just not capable of doing that. China at its peak was producing one every week of coal-fired power plants, which are much simpler than a nuclear power plant. Okay, replacing all that power with wind. This is the largest wind farm in the world. It's planned capacity. It's not finished. We have to build one of these every 2 days. Solar, if we replaced all our power with solar, we would need an area greater than India. It would be the 8th largest country of the world. A fusion reactor, as you recall, what I said is it does produce low-grade radioactive solid material waste every year. By low grade, they mean you only have to store it and keep it separate from society for 100 years, not thousands of years and tens of thousands of years. That's low grade. That's what they mean by low grade. Okay, we would have, if we could run everything on this, we'd have 1.5 billion tons of low grade waste in storage. Where every year you're putting in, you're taking out the oldest stuff and you can reuse that stuff, and then you're putting in the stuff that you generate that year. Okay, this is from a guy who is a fusion. He's invested in a fusion method. Okay, and then we saw this thing, all EV fleets worldwide, demand for metals exceeds the amount of metals that are actually available to us. So lessons learned: we have never replaced an older energy source with a new one. Like I said, and efficiency has never reduced energy consumption. An initial pulse of growth it may not be sustainable. We will not be able to replace fossil fuels with alternatives by 2050. And everybody knows that. And that's why they're no longer, they used to talk about getting to zero, but now they're talking about net zero. And we don't, none of those plans to do net zero are viable. And so what can we do to avoid disastrous climate change, biosphere collapse, and then ultimate collapse of civilization? And that's where we get well, okay, the next talk I'm going to talk about that, but I will tell you that we need degrowth. We need to go all the way back here. I mean, people like Jason Hickel are absolutely right. If I go all the way back and I say, instead of trying to replace all of this stuff with solar, wind, or anything else, we cut our energy consumption, prioritize what we do with that energy so we can, and then bring it down to a level where we could conveniently actually achieve something that we can achieve. Okay, so I'm going to end on that. If you have any questions.